we want to talk a little bit about energy, work, and power. Let's start with energy. What kinds of things have energy? Well, something that's in motion can have energy, kinetic energy, energy due to its motion. If we lift something up in a gravitational field, it can have energy due to its position in the gravitational field, gravitational potential energy. Matter can have energy in the bonds. We call that chemical energy. Electricity is a type of energy. Light carries energy. Sound carries energy. That's a lot of different forms that energy comes in. That can be a little confusing at first, but it has something in common. These seem like very disjointed, separate things, but they all have something in common, and that's the ability to do work. So what is work? Well, we already know that work is a force applied through a distance. Force times distance. So anything that can apply a force through a distance can do work on an object. Work is measured in joules, which is a Newton meter. And energy has the same units as work. Let's take a look at this example. You want to carry this 5 Newton box to the top of the stairs. Its weight is 5 newtons. That means the force of gravity is equal to 5 newtons. And our distance here that we're raising our box is a total of 3 meters vertically up. It turns out it doesn't matter how we get this box from the starting point to the ending point. We could carry it up the stairs and set it there, or we can walk this way and then go up a ladder, or we can throw it. It doesn't matter how it gets there. What matters is that it moved vertically up 3 meters because the force of gravity acts in that direction. So when we calculate the work done, we get 5 newtons of force. Why 5 newtons? Because if gravity is pulling down with a 5 Newton force, and we push up with a 5 Newton force, we exactly cancel it out, and the box can move at constant speed vertically upward. So let's just assume we're moving the box at constant speed. It's not moving faster and faster as we go up the stairs or slower and slower. We're just going to move it at a nice constant speed. So we would have to exert a force to cancel out gravity, 5 newtons. We multiply that by our distance, 15 Newton meters, and we know that a Newton meter is a joule. 15 joules. The thing with work is that it doesn't matter how long it takes me to move this box up to the top of the stairs. I could move really slow and take 10 seconds to make it to the top of the stairs, or I could go really fast and take 2 seconds. And the work done is the same in either case. But it might be important to you to know how fast something is doing work. Maybe when it comes to motors and engines, if you have 2 motors, they can both lift the same weight, but one of them, it takes a long time to lift it up high enough where you can put it on your table. The other one can lift that weight very quickly, and then you can set it on your table. That might be important to you. Maybe there are 2 cars that have the same weight. They're both stopped at the metering light waiting to get on the freeway. They're at rest. The light turns green. They both accelerate up to the same speed, up to freeway speed. But one car can do it in 4 seconds and the other car takes 8 seconds. That might be important to you to know that. That's where power comes in. Power is work divided by time. Units for power are joules per second, which is a watt. You have to be careful with these units because capital W is something that shows up in other places too. We use W for work and we use it for watts, and some people like to use W for weight, the force of gravity. So lots of W's. You just have to be careful when you see one. Make sure you understand the context. So let's take a look at this case. If we take 10 seconds to run up the stairs, our power is going to be 15 joules, 1.5 watts. And in our fast case, we are 5 times more powerful because we did the same amount of work in 1/5 the amount of time, 7.5 watts. Now, watts is not typically a unit we see in the United States when you're looking at motors and engines and cars. Typically, we see horsepower. 1 horsepower is approximately 746 watts. So that means that even in our most powerful case, 7.5 watts is not very much. That's approximately 1/100th of a horsepower. These are tiny numbers. But remember, you're not just moving the box up the stairs, you're also moving your entire body weight up the stairs. There's one more point we need to talk about when it comes to force, distance, and work done, and that's the direction of the force. If our object is moving to the right, let's make it a cart with low friction wheels, and we push on it in the same direction that it's moving, well, what's going to happen to our cart's speed? It's going to move faster and faster. It's going to have more kinetic energy. So the work done on the cart would be positive because its energy, the cart's energy, is increasing. The cart's kinetic energy increases. It moves faster and faster when we push on it in the same direction that the cart's going. If we push in the opposite direction, if our cart is moving to the right and we push to the left, well, what's going to happen to our cart's energy? It's going to slow down. It's going to lose kinetic energy. So in this case, the work done by our force on the cart is negative. When the object's kinetic energy increases, the work done on the object is positive. When the object's kinetic energy decreases, the work done on the object is negative. You could almost say the cart is doing work on us instead of saying we're doing negative work on the cart. Now, what happens if we push perpendicular to the direction of motion? Our cart is moving along to the right, and we put a force pushing down on it like this. Well, that doesn't change the motion of the cart at all. The cart's just going to keep moving with the same speed. So in this case, what's the work done? The work done is 0 if the object's kinetic energy doesn't change. And very shortly, we'll learn how to do this mathematically using vectors.